Hi, this is Tim Hallbach from the National Weather Service in Milwaukee with part 3 of Storm Spotter training from 2016 on observing thunderstorms and the basics that you need to know with thunderstorms. So, in the entire storm spotting process, this is what we consider kind of our fourth step here with observing severe weather, what kind of things you can start to look at to report to the National Weather Service, things that we find important to us. A little bit of background on thunderstorms. Most storms go through a life cycle where, say in the afternoon, you start getting the clouds that start having this kind of towering look to them. That's a key that, a clue at least, that air from the ground is going up and helping to form the cloud and starting to, if it has this kind of towering look to it as opposed to just kind of a flat look, that's a good sign that there could be some storms later on in the day. As it gets to the mature stage, there's air that's both being pulled off the ground and helping the air move up into the thunderstorm. We call this the updraft. So it's actually a wind that is going up through the thunderstorm. And it helps to suspend rain and hail up in the top part of the thunderstorm until it kicks it off to the side here, and you get the other part of the thunderstorm, which is considered the downdraft. So this is the air that's coming down to the ground, hitting, and then pushing out sideways and causing some outflow here. This is the leading edge of where that colder air is coming in off the ground. As long as these two things, the updraft and downdraft, can remain separate, you can have a longer lasting thunderstorm and a much more likelihood that there's going to be severe weather. There's also the dissipating stage, so when that cold air finally chokes off any of this air going up into the thunderstorm, you get to the dissipating stage. It's all just whatever's been suspended starts falling to the ground. It's just a rain shower, and within a short amount of time, this rain shower is gone. The clouds have more of a wispier appearance at this point, as opposed to at the mature stage. They're a little bit more ominous because there is so much rain drops and cloud blocking out the sun that it looks a little bit darker if you're underneath it. Some time lapses here. So this is the updraft. This is air showing how the air makes round after round going up into the thunderstorm. The more that this can happen, the more likely it is that you can have a strong to severe thunderstorm here. And once that air gets chopped off from going up into the thunderstorm, these updrafts stop and the storm stops building. So as long as that can remain separate, you have a chance for some strong to severe weather there. From further away, the structure, what we call this is the main storm tower. So this, if you're a little bit further away again, this is just what you would see in real time, as there's just air going up into the thunderstorm and helping it to build up into this larger storm here. The other part of it is the downdraft or downburst or microburst, depending on what you want to call it. This is from Arizona, but shows it nicely how all of a sudden that rain makes it down to the ground after it was suspended up in the top part of the storm, and poof, hits the ground, and you get some strong winds with something like this. So this is what we consider the downdraft or the downburst portion of the storm. Watch it one more time here. You kind of make the outline out of this pocket of rain. As soon as it hits the ground, get some strong winds with something like that. So when we're forecasting thunderstorms, we look at three different things. Moisture. The more moisture you have available, the more you can make clouds and thunderstorms. So we generally look at the Gulf of Mexico and whether or not we're getting any kind of feed of moisture off of the Gulf to help fuel thunderstorms. And if we do, we could have a lot more. Instability is just our measure of how fast air is moving up to make that updraft, how fast that updraft speed actually is. So the analogy we use is a hot air balloon. If you've ever flown in one of these, you know that there's fire here to help warm the temperature of the air that's inside the balloon here, so that it's a bigger difference between the colder air that's around it here. The bigger the difference, the faster it can move up. Same thing happens with our atmosphere. And then the final ingredient is lift, something that's going to act like a wedge to start getting that air to start moving up into the thunderstorm. So a lot of times it's a cold front or some kind of air mass boundary, if it's a lake breeze, something like that, just to get that air moving up. The bonus ingredient that we look at when we're forecasting thunderstorms for severe weather is wind shear. So there's times where your winds will actually be changing from the ground to the top part of the thunderstorm. So when they're lighter at the ground and then faster, higher above, that helps to tilt the thunderstorm so that that air getting off the ground stays separate from the air dropping back down to the ground. So the more wind shear we have, the different type of storms we can make. So say that we don't have a whole lot of wind shear, most of our storms end up being these single cell type thunderstorms that don't produce a whole lot of severe weather. Once you have a little bit more wind shear, you can start getting these multi-cell clusters or lines of storms. And then when you've got a good balance of both directional and speed shear, so it's changing both in direction and height and speed with height, you can get a supercell thunderstorm, which is one of the worst types of thunderstorms we can get. The single cell storms are pretty short-lived. Typically we don't get a whole lot of severe weather with it, maybe some small hail and some gusty winds. There have been some times where we get some brief weak tornadoes, but very hard to warn on any storms like this, and typically won't because we won't get the larger hail or winds from this type of setup. The most common type of severe weather that we get in Wisconsin is with these multi-cell clusters or squall lines of storms that we get. A lot of damaging winds, some of the different types of storms we can get a lot of large hail, sometimes some brief weak to strong tornadoes, but for the most part the damaging winds and hail are the main concern with a storm like this. The transition that we typically see with a type of squall line we call the bow echo. So when there's a part of a storm, if I go back here, you can see on radar this got this kind of bow shape to it, and when we have something like this, there tends to be really strong winds at the leading edge of the bow, so we look at that area for where there's potential for some stronger winds. The evolution of something like this, you tend to have a little bit of storms, and with time it has such a big area of cold air that's associated with it that keeps pushing out into this warm, moist air that you get this long line of storms that last for quite a long time. Technical definition of a derecho is when there's damage from a storm like this of over 100 miles. So we don't classify that until after the event is done. So one of the features you might be able to see with a storm like this is a shelf cloud. You do not need to report that because we do not know the difference between one shelf cloud and another, and whether you can get severe weather out of one and compared to another. It looks really cool, but unfortunately we can't gauge anything from it, so you do not need to report shelf cloud to us. Here's a time lapse of a shelf cloud. It marks the leading edge of that colder air, the outflow from the storm, moving away from it. This is from Appleton, from Adam, back on July 18th in the morning with the shelf cloud coming in. You can see storms in the background here, the rain, lightning, and all that. So this is just marking the leading edge of that storm coming at you. Another variation of this is a roll cloud. So you can see this is separate from the cloud base like the other one was, but it's the same thing. People have called this in as a tornado in the past because it has that rolling look to it, rotation, but it's sideways and stretches all the way along the horizon. Pretty rare that we get something like that around here, but it is possible. Squalling tornadoes are very hard for us to warn on, and there will be something that you will not be able to see. So we're not expecting people to go out and try to spot tornadoes that are within the squall line here. This is an example from, we had the Verona tornado occur back in 2014, and there was a EF3 tornado that occurred with something like this, and it was back within all this rain here, so you never would have seen it. And just best to take shelter when something like that occurs. So do not try to view a storm like that. The last is the Supercell Thunderstorm. So the balance of all the worst severe weather ingredients we can get. This is from Fairdale from last year, a picture from Tom Purdy of around that time. This is a typical look to what these supercell thunderstorms look like on radar, where this is our hook echo, where the air is going up into the thunderstorm and actually rotating around with it. All your rain, heavy rain and hail is on the north side here, where the reds and pinks and purples are. And then down here is where the tornado typically is, down on the southwest side of these storms. This red area right in here is actually a debris ball from the tornado hitting a city down in northern Illinois down there. So this is typically what we see with supercell tornadoes. These days are very rare, but we can have these, and a lot of our big tornado days have been when we've had supercell thunderstorms. It also can produce some of the largest hail. This is a hailstone from Vivian, South Dakota from that day, with an 8-inch hailstone that occurred there, which is the U.S. record. So just a schematic of what these storms look like. If you're on the south side of the storm, that your air is pulled up in this area on the southwest side and goes up into the storm, and your downdraft is on the northeast side of the storm. So what helps to keep this going for so long is that this air going up into the storm stays separate from the air going back down on the northeast side of the storm for a long period of time, thanks to that wind shear that occurs. But the main features you'll want to look at will be on this southwest side here, the wall cloud and a tornado, and we'll talk a little bit more about that in a little bit. Here is a picture, kind of a similar schematic here, where you've got your air going up into the thunderstorm in this part. The dark area in here is where all the rain and hail might be falling, and then right in here is the feature you want to be looking at, which is the wall cloud and possibly a tornado there. From space, how the schematic looks, again, like that radar shows, the T here is where the tornado might be. You've got your hook echo right here where it's dry because the air is coming in here. There's no rain falling down there, and it's getting pulled up into the thunderstorm, and the rest of the rain and all that falls down to the northeast side of the storm. So you're not getting that air falling right on top of where the tornado might be, or where this air is going up into the thunderstorm. So good spotting locations on a storm like this, if it's moving off to the east, anywhere really along the southern edge of where the storm might be is where you'd like to be able to look up and see those features coming at you. If you're out ahead of it, might not be such a good spot to be in, so time to seek shelter or get out of the way of a storm like this. The rain-free base is just this area that we're talking about, where you're going to be able to see the features, where you're going to see the wall cloud, maybe a tornado develop as well, just down in that southwest area. The wall cloud, this is an isolated lowering that's on the rear of the storm, the southwest side of it. Some people will confuse this with the shelf cloud. Just remember that the shelf cloud is always out ahead of the storm, moving away from it, while the wall cloud is this isolated lowering on the southwest side of the storm. Watch it to see if it's persistent and whether or not there's any kind of rotation with it. And just because there's a lot of cloud movement doesn't mean that there's rotation with it. Every wall cloud that you're going to see is going to look a little bit different, so just know, especially in Wisconsin, they look, can look any different way. So here's one from Tom from Footville, where you can see this little isolated lowering here, and if you were to see this in real time, there'd be motions from the left to the right in the front, and then right to the left and back. Another one from Hunter Anderson over by Roxbury. This is a time lapse, and initially we were wondering whether or not there was a tornado that occurred there, but that ended up being a Scud cloud, and we'll talk a little bit more on that in different parts of the spotter training. But if you watch the rotation here, you can see the wall cloud and how different this looks compared to other wall clouds that were just pictured before. So watch the top part of this time lapse. You can see left to right in front, and then right to left and back. So this would be considered a wall cloud here. No tornadoes occurred, but this is where the air is all going up into the thunderstorm. A funnel cloud, this is technically rotation, a funnel that's at the base of the cloud, but the rotation from that's not making it all the way down to the ground yet. So with your terminology, if you're going to report a funnel cloud, just remember that this is not in contact with the ground yet at this point.